All right, so here's our plan for today. When we were together last, you took a quiz, and I have that quiz to return back to you. If you missed that quiz, then if you want to do it during our work time, just so you have that experience, you're welcome to. Otherwise, the formative grade will be replaced by the summative. So, totally up to you. Your choice for what kind of feedback you want to get. This is an interesting unit, and in fact, if you'll do me a favor, flip to the graphic side of your warm-up, because if you go to that, the last unit, the last lesson we had and this lesson are going to feel like they don't really fit in. But what I want you to understand is what we're talking about for this whole unit is just what can we do with this derivative? Now that we know how to find derivatives, and that's what Unit 1 was about, understanding limits. Without the limits, we can't get the derivatives. Units 2 and 3 were about taking all different kinds of derivatives, using the limit definition of the derivative, and then discovering the power rule, the quotient rule, the product rule, the chain rule, dealing with e's and logs and trigs. All of that stuff needs to be in the front of your brain. So somebody even last class came up and asked me a question, and my head wasn't in it, and I had to go back to my notes to remember how to take the derivative of either an exponent, a log, a trig, and you need to know all of that stuff is fair game. So that's what we were talking about with units 2 and 3. How do we take all these derivatives? Where do we get them from? Unit 4 is about applying those derivative concepts. So this graphic helps me understand that not everything is necessarily related. We're kind of in like, picture yourself in Target. Like if you go to Target, you could be getting groceries, but you could be getting clothes, or you could be getting school supplies. So one doesn't necessarily lead to the other. You can go shopping in a different unit for different conversations. That first conversation in Unit 1 was where, in Section 1, it was where we were talking about interpreting in context. Some of you, when you give your quizzes back, you're going to be pretty fussy because I was fussy about units. If you're taking the derivative of a rate, then you need to know that it's the measure per unit squared, because it's the feet per second, or because you're looking at the rate of a rate. So if you didn't take the time to tell me whether something was increasing or decreasing because of that positive and negative sense of that rate, you want to make sure that you definitely pay attention to that. So that was 4.1, talking about that. When we talk about the derivative, you need to think about these three synonyms, and it's interesting because they're not really synonyms. It depends on what I'm talking about. If I'm talking about the derivative, that's in that one sense of looking at that slope of that tangent line. So if I'm asking about the derivative, that's that d of that function over dy, the change in something compared to something else. So whether I'm talking about an instantaneous rate of change, whether I'm talking about the slope of the tangent line, or that derivative value, or the equation to give you the derivative at any input value, those will be subtle nuances. Some of you told me that something was negative because the slope was negative. No, the slope of a curvy graph doesn't have a slope, but it does have a tangent line, and that tangent line has a slope. So we need to make sure that we're tight about what it is we're talking about when we're talking about these interchangeable terms that definitely are more applicable in certain situations than others. When we talked about position, velocity, and acceleration, what I want you to do, I'm going to go through and talk about each of these units. Scribble down some notes of things that you think matter in this box. The relationship between position, velocity, and acceleration, and where the derivative and the second derivative play into that. This other rates of change was where we were exploring things with a calculator. Then we started talking about related rates. And these all things felt like they were telling a story, and then all of a sudden we're talking about local linearity. Local linearity doesn't have anything to do with related rates. So just because this section came after related rates doesn't mean one is a prerequisite for the other. Local linearity is a separate conversation of, hey, now that you know how to find the derivative, check out what you can do. And the same is going to be today when we talk about l'hôpital. That's pronounced not la hospitals, it's l'hôpital. And we're going to talk about l'hôpital's rule. And l'hôpital's rule doesn't have to do with local linearity or related rates or other rates of change or position, velocity, acceleration. Are you ready what it has to do with? Limits. Indeterminate limits. So remember when we used to have to find the conjugate, or we had to factor, or find a common denominator? That's a shortcut to all of that noise that we had to do a couple of months ago, but we couldn't figure out the shortcut until we knew how to take the derivative. So that's what's coming today. So what I want you to think about is each of these columns as a separate application of this tool that we now have. Now that we have this finding the derivative, we can talk about this, we can talk about this, and this test is harder in the respect of it seems like just a potpourri of a collection of different questions. They don't all naturally relate one from the next. So we want you to think about little buckets or little columns that each of these applications of the derivative, that's our overarching umbrella. Does that make sense to you? All right. So go ahead and take out your packet, because whether or not you find this valuable, maybe somebody else in the class does, because I enjoy going through and talking about our unit as a whole. So when I look at where we are, we can go ahead and talk about each of these conversations, and you could go through them as a whole. We started off the unit where we practiced figuring out independent and dependent variables. We practiced figuring out what was changing, what we were measuring, and then practicing with the units. And that's a really good habit, that you want to make sure that when you're giving an answer, that you're giving a full answer in terms of rates increasing and decreasing and including a lot of units. So this first section of the unit was really about just developing really good habits about full answers with input units, output and units, and then telling whether something is increasing or decreasing at whatever rate. As you flip through this packet, and again, I'm not collecting the packets to determine how much homework you have or have not done, because there's a plethora of resources for you. This whole packet, all the corrective assignments, the warm-ups, and we're not even talking about AP Classroom yet. But your understanding of this content is really about at-bats. How many problems have you done? And once you do enough at-bats that you know how to do that kind of problem, stop doing it. So if you don't need to practice finding the derivative using the power rule anymore, don't practice those. But maybe you do need to go back and practice exponents or logs or trigs, because that'll be where you need to spend your time studying. So whenever you flip through your packet, if you see a time where you said no thank you to the homework, make sure that choice doesn't bite you in the butt when you sit down and take the test, because everything is fair game, including stuff from packets from units 3 and 2 and 1. So you want to make sure you're good on that. All right. We started position, velocity, acceleration, tossing Beanie Babies in the air, talking about the difference between this Beanie Baby going up and down versus this graph that has this arc to it. And we understood because time is on our axis, that Beanie's position, its height over time, ends up giving this lovely arc. When we take the derivative of position, we get velocity. When we take the derivative of velocity, we get acceleration. And when we talk about these higher order derivatives, understanding those relationships is important, especially what happens at these critical values. When my velocity is equal to 0, that's my Beanie Baby suspended up in the air. So we like to get kind of tricky with you where we give you different looking graphs and you have to stop for a minute and ask yourself, wait, what am I looking at? Is this a position graph? Is this a velocity graph? Because the rate of change of your velocity is acceleration. But when you're talking about velocity, anything above the x-axis is where it's increasing, anything below the x-axis is where the function is decreasing. And our conversations are always going back to that original function unless otherwise specified. So the whole conversation about velocity being positive and negative and how it's moving and where it's at rest, and then our average versus our instantaneous velocity, and that displacement, looking at that distance that we travel. If our velocity changes sign and we're traveling in a different direction, we need to know, are you talking about our net change in position? Because if that's true, then the most I walk all day is the distance from that door to my desk. But if we're talking about my total distance traveled, I need to get some absolute values and count all my steps that I'm taking throughout my day. So that's an important conversation. For some reason, the word particle just gets me. It takes me to like chemistry or physics, and I would much rather stay in calculus. So if it's easier for you to think about the beanie traveling or a car traveling or something like that, it's anything that's in motion. The biggest thing here is that we understand that if our velocity is negative, that just means that I'm moving in a left or downward motion. So make sure that you've done this practice and checked your answers, that you pay careful attention to the graphs that you're reading, and that you're double checking whether or not you are doing things like displacement and velocity correctly. All right. For our warm-up, we did an extra assignment. These CA stand for corrective assignments, and it's an additional practice that we did together. We talked a lot about this graph here, making sure that we're looking at the velocity, and then here they're asking about acceleration. So when we're talking about acceleration, we're talking about the rate of change of the velocity. But we had that conversation about if our signs match, what does that mean? If our signs are different, what does that mean? Versus speeding up or slowing down. So you want to make sure that you're clear on those big ideas. In this conversation, we ended up going back and revisiting conversations with the calculator. Make sure you remember where Math 8 is. A couple of you on the quiz tried to do some awful lot of work with a really yucky problem that said use your calculator. Use your calculator, use your calculator, because that's as simple as knowing how to plug in something and getting the derivative of a function. And this is where we were talking about when we're asked to estimate an instantaneous rate of change. Our average rate of change can provide that for us if we find the narrowest field. Making sure here you recognize these three choices are all going to give us different answers, and how I go about doing that as long as I show my work. So the showing your work becomes an interesting conversation. An answer without work doesn't justify why you did what you did. So make sure that you practice these problems with the calculator and that you understand those keystrokes. For our next lesson, we reviewed a lot of formulas. If you have that formula sheet and you're continuing to work on them and add to them as we go, I don't know if we've added any or not to what we came up with originally, making sure that those formulas are in the front of your brain. If we give you something off, if we ask you a question about something off of that, chances are we'll give you the formula, but you can all say thank you to me now. You're welcome. Mr. Logan wanted to put a question on the test that had to do with similar triangles changing with the shadow of a person walking, and I'm like, we haven't given them any of those questions, and we haven't gone over any of those questions. And he's like, they should know similar triangles. They've known that since we taught them that in geometry. I'm like, they can't remember bringing a pencil to class. Do you think they remember what we taught them in geometry? So I talked him out of putting that one on the test. So what are you going to say to me?
Thank you.
Yeah. But guess what we're practicing after? Because we're looking at the problems on the test. And I'm like, we can't do that. We haven't done any of those. So we want to make sure that we introduce similar triangles and ratios and all those things that he thinks you remember from. See, he thinks that you guys are just so smart. And he's like, of course they remember those. I'm like, of course they do. All right, so we went ahead and we did another calculator question problem. In 4.4, we're talking about an introduction to related rates, and we're talking about setting up a scenario that's true. Some of you are going to be grumpy with me about your Pythagoras conversations on the quiz, because if you're asked to set up a relationship between the variables, you have to make sure you consider all the variables that you have. So if we have a question like these police cars going and whatever rate they're going, the conversations about if you know something is constant, you do put the 0 in. So a couple of you didn't put the 0 in for the ladder, so that counted against you. Like, for example, this airplane's height was constant. So that's 0, and that shows us the relationship between the variables in simplest form. Some of you mixed up which variable the ladder represented, so we'll go back and look at that if you need more help. Looking at how to draw pictures and look at the directions that things were going in. I'm assuming that the angle of elevation ones are the ones that are trickiest for you. So make sure that you go hunting for them. You can go online and find the unfilled in versions of all of our notes and then practice them and then go back and compare. So if those are the ones that are dicey for you, those are the ones that you make an effort to seek out and practice. Don't go back and practice what you already know. If you're good with cylinder tanks filling up and water sinking and what's constant and not constant, then don't do those. Spend your time working on where you need help. All right. Then for our next warm-up, we ended up drawing a bunch of pictures for how things change. If we have a ladder against the wall, the ladder is the constant. Unless you have a shrinking ladder, which that would be disastrous. But pay attention, they do exist. But make sure that you pay attention to which of your variables is constant and which is changing. The baseball runner, this distance from home plate to first base is changing. Somebody came to me and asked me a question about how do I know whether the rates are positive or negative or not, and it totally has to do with, is it growing or shrinking? So in the one scenario where we had the, where was the one where we had the two cars driving towards each other? And then the conversation about how do you know if they're going east or west, or if it's positive or negative, because the student was thinking to the left is negative, to the right is positive, which is true for a particle on a horizontal axis. But when we're talking about police cars and bad guys, if the bad guy's distance is increasing away from the police car, his rate's going to be positive. If the police car, or one where the two airplanes were flying towards each other at the same elevation, both of their rates are going to be negative because the space between them is shrinking. So you're allowed to take some liberties there with understanding, as my ladder falls down the wall, my distance is shrinking. As the base moves away from the wall, that distance is increasing. So understanding what's happening to your shape in a positive or a negative sense, paying attention to growing or shrinking is important for the sign, positive, negative, of your rate. Those related rate problems are going to be ones that you want to make sure that you practice. An ice cube melting, you want to make sure your rate is going to be negative. I wish I could find that airplane one. Oh, maybe here it is. Where we have, yeah, and this air traffic controller, where our airplanes were flying towards each other, the space between them, that triangle that they create, is shrinking. So each of their rates. Now the way I have it drawn, the one airplane is going left and the other airplane is going down. But I can actually get away with drawing this diagram. If I wanted to do this one airplane was going this way and this airplane was going this way, someone would argue that their rates are positive because they're moving in a positive direction. But if you look at the triangle that's created by these two airplanes, that triangle, as they fly closer and closer to each other, is shrinking. So because that's shrinking, their rates are going to be negative. Does that make sense to you? All right. So then, when we were together last, we talked about approximating with local linearity. And again, you're like, what does this have to do with related rates? Nothing. Different department of the same store. So what we're saying, hey, now that we know how to find this derivative, we can go ahead and find the equation of the tangent line, and we can know that if our curve has a value that we want to know, if it's super close to where we write the equation of the derivative, we can go ahead and use this. And then we can know whether our conversations are over or under estimates by looking at the concavity. And the concavity is how the graph is shaped. And we're going to talk about this more next unit. If the shape is up like a cup, it's a positive concavity. If it's down like a frown, then it's a negative concavity. So even if you just draw this picture, if I want to know what's happening on the curve super, super close to this line of tangent, or to this point of tangency on either side of this, I could use that red tangent line to estimate a value that's pretty close. But because my graph is concave up, I know that my tangent line is going to be an underestimate. If I have a concave down graph and I want to know what this value is, I can use the tangent line, and I can know that that output value that I have estimated is going to be an overestimate. All right, and that's what brings us up to today. So here is your warm-up, dealing with some more practices of local linearity. I love the corrective assignments because the answers are right here on the bottom. Super cute and fun. All right. If I said anything of any value during that last 20 minutes, what I'd like you to do is share maybe what you wrote down in each column, which you thought was a valuable conversation with your partner, and talk about things that you know you need to go back and spend more time on studying. Take a minute and do that right now. Turn to your partner, go. We'll come back and talk about that if you want. But what I really want to do is button this up and have our last conversation about l'hôpital. French dude who came up with this pretty cool application of the derivative. And lots of kids are like, man, why didn't you tell us back when we were learning about indeterminate limits months ago? And I'm like, yeah, but you didn't know what you didn't know. It's kind of like Dorothy in the red slippers. She had to go through all of that drama to know that there's no place like home. So they didn't tell her about it till the very end. Are you with me on the red slippers? All right. Take take your brain back to limits. The very first rule when evaluating limits is always plug it in. So we always are going to use direct substitution. So if somebody says, what is the limit of this function as x approaches 3? Remember, what we love is when the limit from the left and the limit from the right and the value of the function are all the same. So when I go ahead and I plug in that value for 3, I can have 2 times 3 minus 5 over 3. So 6 minus 5 is 1, and I end up with a lovely limit of 1/3. Nothing crazy, nothing janky, nothing going on. All I do is plug and check. And what's hard is when we've been doing this level to take our brain back to, oh yeah, that was easy, just plug it in. We good with that? When we started to talk about different levels of our rational functions, we ended up having some times where we ended up with an indeterminate form. And that indeterminate form, when I plug in, if I took 2 squared minus 7 times 2 plus 10 over 2 minus 2, I ended up with a 0 over 0, which we knew you can't do. So we knew that that plugging in strategy wasn't going to work for us. What we learned instead is to go ahead and take a look at this limit and say, okay, if I took the limit as x approaches 2, can I maybe factor this? Can I have an x minus 2? Can I maybe call this an x minus 5 as a factored form and recognize that I can go ahead and cancel this out? And then take that limit and say I'm going to plug in that value and recognize that I wind up with -3 as my limit. And that was super cool because we practiced lots of factoring, we practiced conjugates, we practiced, let's see, what else did we have in our toolbox? We could factor, we can find a common denominator, or we can find a conjugate. They were our tools whenever we got a 0 over 0. So you remember those conversations. L'Hopital's rule says, instead of dealing with all of this, what if I gave you a shortcut? What if all of this you didn't have to bother doing? If you ended up with a 0 in your numerator and a 0 in your denominator when you plugged and chugged, and you ended up with this indeterminate form, either with 0 over 0 or infinity over infinity, what you can do instead is, if you're finding the limit as x approaches a of g of, or f of x over g of x, you can go ahead and take the derivative of f and the derivative of g separately. So if we listen to L'Hopital and we're like, what is that going to work for us? I can go ahead and try his new funky way. I can say, if I take the derivative of that, I get 2x minus 7. If I take the derivative of my denominator, I get 1. If I plug in a 2, then I get my -3. So if you're like, put your shortcut away. I ever do so love a factoring conjugate common denominator problem. Right on. But if you're like, I don't have time for that, L'Hopital saves you crazy time, especially when you're taking a test in May that is timed. So it's a worthwhile shortcut. It has, what does this have to do with related rates? Nothing. What does this have to do with local linearity? Nothing. What's this have to do with derivatives? It's another application. Sound okay? And that's it. All you have to do is take the derivative of the numerator, take the derivative of the denominator. Now what's kind of cool is they gave us some examples here where you're like, don't you love a simple rule that when the first time you try to do it, you're like, hey, this isn't working. So let's pay attention to these four as we worked through these different ones together. If I'm plugging in 2 into this limit, 2 minus 2 is 0, 3 times 8 is 24, minus 6 times 4 is 24, plus 2 minus 2, I get another 0. The first thing you need to remember is that it only works in our indeterminate, I hope I spelled that right, I don't know, limits. When you get 0 over 0, when you're taking a limit, go to L'Hopital and he can make it work for you. I'm going to go ahead and take the derivative of my numerator. I'm going to take the derivative of my denominator, if I can remember what 3 times 3 is. And I'm going to go ahead and substitute my value in. So if I have 1 over 9 times 2 squared minus 12 times 2 plus 1, I can recognize that that limit of that function as x approaches 2 is going to be 1 over, what's that, 36 minus 24 plus 1 is going to be equal to 1 over 13. And we got to do that instead of factoring, which is pretty cool and super quick. So if your approach, yeah.
When you do the derivative, you have to write the derivative sign for the limit sign in front of it.
So what we're doing is a shortcut. So when we're using L'Hopital, we're not taking the limit, so we don't write that. We are taking the derivative, which is an operation, but we don't have an equal sign or anything. So we're going to do this work, and we're going to box this answer, and this justifies that. So it's a shortcut kind of thing. Are we okay with that? That's a great question, because we get to just take the derivative. We're stepping out of the limit. All right. Limit as x approaches 0. When I plug this in, the sign of 0 is equal to 0 over 0, and that's our indeterminate form. So we need to make sure we do that. Now you have a choice. You can do your trig limits, and maybe if you've been studying and reviewing, you're like, oh, I remember this one. Anybody? Yeah, let's use L'Hopital. And we can go ahead and figure out this limit. What is the derivative of the sine of 6x? I heard it. The cosine of 6x, and what are you going to remember? Chain rule, right? What is the derivative of x? 1. So now we're going to go ahead and plug our value in. the limit as x approaches 0, I want the cosine of 6 times 0 times 6. 6 times 0 is 0. Cosine of 0 is 1. 1 times 6 is, voila, and done. Now, maybe you remembered that the sine of x over x, the limit as x approaches 0 is equal to 1. And then remember you had to do that fun stuff where you multiplied this by 6 over 6, so you got 1 here, right? Oops, let me change where I drew my circle. You got 1 here, and that left you with 6, remember that? And then you still get 6 there, no problem. All right, let's talk about 4. So when I take a look at 4, something interesting happens. Go ahead with your partner. Plug it in, get the indeterminate form, pretend like you, or just go ahead and apply L'Hopital. Go. Your mark is set, go. So Piper just asked the same thing that Grace did, and I think I'm going to change my answer because of this conversation. When I plugged in 0, I get 0 over 0, which is the indeterminate form, and that indeterminate form lets me use L'Hopital's rule. But the interesting thing is what ends up happening here, when I go to plug 0 in, I still get 0 over 0. So I'm going to change my mind, Grace. You can have a Smartie. And I'm going to go ahead and I'm going to say that when you do L'Hopital's rule, we're going to rewrite the limit until we go to plug in. So we're going to rewrite the limit until we plug in because of this happening. When I go to plug in, notice when I put 0 into the sine of x over 2 times 0, I still get an indeterminate form. And you're like, what the heck? That's a stupid shortcut. It doesn't work. Sure it does. You get to do it again and again and again. It's like the shampoo bottle that says lather, rinse, repeat. If you end up getting a 0 over 0 indeterminate form, you can go ahead and take that derivative of my numerator and denominator again. So you can go ahead and say, all right, the limit as x approaches 0, the derivative of the sine of x is the cosine of x. The derivative of 2x is 2. What is when I go to plug in, the cosine of 0 over 2, cosine of 0 is going to be equal to 1/2. Ariane, what's up? I forgot what?
The negative of cosine of x.
Why do I need a negative?
Can you find the derivative of
Sine to cosine is positive. Cosine to sine.
It's okay.
Remember, it's every time you see the C, you're like, oh crap, that's negative. But thanks for checking in. That's a good double check. Now, what's interesting is you can see what makes this polynomial's limit an indeterminate form. And notice when I take each next derivative value, my power of x goes down, 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 down. So if I have an x in the denominator that's causing this to zero out, each time I take the derivative, it's going to eventually disappear. So I'll eventually power out of those x's, which is good. All right, back to limits. And yes, you're going to have to spend some time talking about limits because this is a conversation about which function grows faster. Remember, we talked about exponentials, and then we talked about powers, and then we talked about our logs or snails, right? So we're talking about as x approaches infinity, what's happening to my function. So we can't plug infinity into either of these. We get an indeterminate form. Unless we can remember what happens with my power function versus my exponential function. But let's say I can't remember that rule. L'Hopital can help me here too. The same as here, I eventually lost my exponent. Do you see how that's going to end up happening here too? So go ahead and with your partner, talk about and try to do this one and see where you wind up and if we're the same. All right, so just so you can follow my work, here I went ahead and I took the derivative of 2x squared, and that's what gave me 4x. The derivative of e to the 2x is going to be e to the 2x, and don't forget your chain rule. I simplified that here by canceling out my 4 and my 2, and that's what gave me 2x over e to the 2x. And again, when I plug infinity in, I get infinity over infinity. So if I can't remember which infinity is growing faster or what happens, I can apply L'Hopital one more time. So after I simplify this, I still get the indeterminate form of infinity over infinity for each of these times until I take the derivative one more time. The derivative of 2x is 2. Now again, look how my x's are powering down. I go from having x to the second power, x to the first power, and then here I have no x's left. So I'm not going to get infinity here. Instead, I get 2 over infinity. And that larger the my denominator gets, the closer I approach 0. So that limit, that end behavior is going to be 0. Are we good with that? Okay. Here's where they'll try to jack you up. And one of the hardest things about this test is going to be when they start mixing everything up together. It's kind of like if you're in a pizza shop, you're getting pizza, right? So the problem is when you're at the grocery store, you have all the options mixed together. When you look at a problem like this, you need to make sure you know that's not L'Hopital. That's the quotient rule. So you're only applying L'Hopital when you have a limit. So if you look at this one, there's no limit. So then therefore, no L'Hopital. So if you don't see a limit, you're not applying L'Hopital. This is just a straight derivative problem. So this is not the trig rule. This is not a shortcut. This is not anything. It's your choice whether or not you want to do your quotient rule or whether you want to rewrite it and use your product rule. Because if you're finding dx, you can do of the sine of 6x times x to the negative 1. And you can do the first times root of the second plus the second times root of the first. Or you can go ahead and keep that as a quotient and say that it's low d high minus high d low, square the bottom, and away we go. Both of those will give you your answer. If you really enjoy this, you can go ahead and my first term times the derivative of my second plus the derivative of my first times my second. What's fun is if you do it both ways and then simplify down. It all works out. Like, you get a weird version of fun. Good times. Okay. So that's L'Hôpital. And that's our last conversation. What I'd like you to do is do me a favor, look on this back and just scan it over with your partner and find the ones that are no L'Hôpital. Talk about it with your partner, go. Do we agree? No L'Hôpital on 6, because there's no limit. And no L'Hôpital on 13, because there's no limit. That's asking you to do the derivative. This is a great example of, do I need to do every problem? Probably not. But if I were studying for this test, I would go through and I would do the limits that I find tricky. So for example, I don't need practice on this or this. I might need review on that. I don't need this. I might need this. I might need this. I might need this. This. Are you with me on the ones I'm picking? I'm picking the hard ones. Maybe, because this is infinity, I would spend my time doing the hard ones. And that's so counterproductive because, like, you totally want to, like, eat the ice cream you like best first, but, like, you already know how to do the easy ones, so you're limited on time. You want to do the things that make sense for you test-wise. All right. For review, I have a couple things for you. In the back of your packet is this review section. In the last 20 minutes of class, you're welcome to tackle this because this gives you a smattering of everything. In addition, I have another corrective assignment that gives you another smattering of everything. In addition, I put on AP Classroom some progress check and a review for you to do. Your choice is how you want to go about doing this. If you need extra support from me, I am after school today. I am after school tomorrow. Some people that are going on a field trip have already made arrangements to come in early tomorrow to take the test. So that's an option for you too. If there are people that are on a field trip today, I'm still expecting them to take the test on Friday. So I'm saying that for the purposes of the video and for you to share with your friends. If they're in school tomorrow, they should come see me for their quiz back kind of thing. I will not be here on Friday. I might be here in the morning, so you can come see me in the morning if you have questions. And I'm probably going to teach my second period class, but I probably will not be here for Stinger, and I won't be here for your class. Kind of a crazy thing that we're doing, but our house is on the Herndon Homes tour this weekend. I don't know if any of your moms or dads like walking through other people's houses, but our house is on the Herndon Homes tour. We live in one of the historic houses on Eldon Street, and they're coming on Friday to video. I have to give a tour through my house on video, so we're doing that while you guys are taking the test. So you're going to come in, you're going to have the 90 minutes to take the test, and then have a weekend free of calculus. So my suggestion is to you is that you go hard and fast on calculus for the next 46 and a half hours, so that when you walk in on Friday, you feel good. I have that little diagram on the board for my sweet little geometries. They are so stuck in the retake loop, it's not even funny. They think because they could do the retake that they can, but unfortunately they're struggling with Unit 4 because they never learned Unit 3 and Unit 2, and those are both still out for retakes. So they're so stuck in the retake loop, it's not even funny. You have to make a commitment to go hard on where your obligations are, and I know you guys are balancing a lot with AP classes and honors classes and working outside of school and sports and other obligations, and I appreciate you being great students, but that's what it's about. So if you need me before school or after school, you know when to ask me questions, but there will be no review or questions before the test on Friday. Sound okay? All right, your time is your own, go.